Hello, today we are doing Paul Hewitt's Conceptual Physics, Chapter 24, Thermodynamics. I love thermodynamics. It has a really cool name. It's fun to say. Well, thermodynamics is talking about the movement of heat. Thermo, heat, dynamics, movement. Sweet, don't do the dishes. It makes such noise. Thermodynamics, we start out by talking about things like ice cubes and hot tea, and we end up by having huge, deep philosophical implications. You'll see how, hopefully we'll get to that and you'll be able to see how. So starting out with, well, what is heat and all that? Remember the vibrations in molecules. Theoretically, you can cool down your object, right? The more you cool it, the slower and slower those molecules are vibrating. And if you cool it all the way down to a temperature where nothing's moving anymore, you can't cool it down anymore, right? The definition of cooling it down means you're taking out that thermal energy when there's no thermal energy left, when it's not even moving. That is what we call absolute zero. Theoretically, there is no upper limit on high temperature, but there is a limit on low temperature, absolute zero. And what is absolute zero in Celsius? It's negative 273, I believe. They like to, now a lot of scientists didn't want to work with negative numbers because it's a pain. And so then they just said, we'll have a Kelvin scale, and a Kelvin is exactly the same amount as a Celsius, but they just call zero Kelvin equals negative 273 Celsius, and that way they only have to work with positive numbers in these equations. Well, anyways, so we are going to talk, so that, think about heat flow, absolute zero. When something's absolute zero, it cannot get any colder. It's not moving at all. Absolute dead, just hanging out there, negative 273 degrees Celsius. Okay, now we're going to talk about the famous 3 laws of thermodynamics. So the first law of thermodynamics, now one thing that's a little confusing is that often people will state these thermodynamic laws in slightly different ways. There's a very technical way to say it, and then we try to say it in a more, understanding way. But you can kind of take that technical definition and say it in multiple ways. So sometimes you'll hear something and you're like, wait, is that the first law of thermodynamics? And if you really think about it, you're like, oh, that is. They're just saying it in a slightly different way. So the first law of thermodynamics is that the heat, well, it's basically that whenever heat is added to a system, it transforms into an equal amount of some other form of energy. So whenever heat is added to a system, it is transformed into that same amount, an equal amount of some other form of energy. And if you remember from last semester, this is really just the thermal version of the law of conservation of energy. That energy cannot be created or destroyed, that it is merely transformed from one form to another form. Like how gravitational potential energy becomes kinetic energy, that sort of thing. Another way to state it is that the heat added in to a system, heat added in, so I'll just write heat added, this is the heat added in to this system, this guy, is the same as the increase in the internal energy. Internal energy, remember, that is thermal energy, molecular kinetic energy. We like to call it internal energy. The increase in the internal energy plus the external work done by the system. Now, a good example of this is you have a little heat piston, okay? So you got your little jar. Running out of space here. Jenny, can they see here on the board?
Yes, they can.
Okay, so we've got our little can here of air, and you have a little piston on you, all right? And you've got a little, you got your little motor, or your little, what's the thing? You've got your little fin thing. And you put it on a fire, you heat it up. Okay, fire, got a little fire here. So we're heating up, and as the molecules, so we're adding heat in, as the molecules are bouncing around, the external work is it's going to push that piston, I guess we didn't really need this guy, it'll push that little piston up. So that's work that's being done, and if you attach it to something, you can actually make it doing something useful for you. But as it's pushing that up, that is the external work done by the system, the increase in internal energy, that will be the same as the heat energy that we added into the system. Now, supposing it can't do work. Suppose there is no piston, it's just a little jar, a sealed can of gas, okay? So now there is no external work being done. It's just a can, it's sitting there on the fire, right? So now that this has gone to zero, we know that whatever heat we add in is just going to result in the increase of the internal energy, bing, 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 of those little gas molecules inside of the can. And if we just keep heating up to the point that this thing bursts open, well, now we have done external work, the work being destroying the can. So this is really just, the first law of thermodynamics is really simply just restating the law of conservation of energy, but in a thermal way. They're in the little yellow box. They have a sample question. And they say here, if 10 joules, so here are ways that heating up that little can can give you some useful work for you. So if 10 joules are added into a system, so we've got 10 joules of heat added into the system here, right? 10 joules of heat added in. And they said, and there is no external work done by the system. How much does the internal energy increase by? Well, 10 equals this plus 0, right? Because they said there's no external work. Well, we know that what plus 0 is 10. It must be 10 joules. And so then they ask another version, like, what if you know that you put 10 joules into the system and it did 4 joules of work for you? Well, obviously 10 plus 4, it must be 6. Then you know that there are 6 joules of increase of that internal energy. Okay. Then he talks a bit, goes on slight digression about adiabatic processes. So adiabatic processes. So an adiabatic process is basically these big blobs of air, like when you, adiabatic process is basically as you change the pressure on the air and like the size of it, then the temperature will change. So you see this in this is why he was talking about how diesel engines don't actually need spark plugs, is that as the piston compresses the air and the gas in the engine, in the diesel engine, it gets so hot just from being compressed. Remember, as you compress that gas, it gets hotter. It gets so hot just from being compressed that it's enough that it doesn't even need spark plugs to start ignition. And here, talk about from a weather perspective, these big, huge blobs of air. As they rise, they're kind of like, think of it as like a giant balloon. As these huge air masses, as they rise, they actually get colder, adiabatically. They get colder, and it's not, not that they're getting radiation or this, that, the other, just from the fact their pressure is changing. Because remember, on Earth, the higher you go up, remember the air pressure lessens as it goes up and it increases as you come down. So for every kilometer that one of these giant air blobs goes up, its temperature cools by 10 degrees Celsius. And every kilometer that it comes down, it heats up by 10 degrees Celsius. So if you had this like giant balloon up high and it could be super, super cold, and you manage somehow to pull it down super fast without it getting to radiate off that heat, it would be super hot by the time it came down. And we see this.
Wait, won't it sink by getting colder because hot air rises?
I mean, if you pull it down like in a balloon. This is the way. Okay, so here we'll see an example of a mountain. This is why when you often see like oceans, and they have a dry side of the mountain and a wet side of the mountain. A green. Often you'll see a green side of the mountain and a dry looking side of the mountain. And this is where the ocean will be. And the reason is you have this air. So say you have this warm, wet air coming off of the ocean. This warm, wet air. And as the winds push it, it's forced to go up the mountain. And as it goes up, well, what happens? The pressure decreases as it goes up, and it gets colder. And as it gets colder, its dew point, the amount of water, as you know, hot air can hold a lot more water than cold air. Cold air can't hold as much water. I mean, that's why if you hang your clothes out to dry on a cold day, they don't dry as fast as when you hang out on a wet day, because the air can soak up the water. So here, as the air gets cold, it can't hold on to its water anymore, and it rains, and that's why you get this green, lush side of the mountain. And it gets up here now, it's dry and cold. Now, as it's forced down the mountain, it heats up, because remember, as the pressure increases, it gets hotter, like that air in the piston in the diesel engine. And so it gets hotter, and you end up with these warm, dry winds on this side. So it's warm and dry here. Here it's cold, and well, here it's cold and wet. because it's dropping its water. And here it is warm and wet. And that is why a lot of times when you see these mountain ranges near the ocean, they have this green lush side and then a warm dry side.
I haven't seen that.
Well, if you go look at like Google Earth and stuff, you can see stuff like that. Okay, so enough about the adiabatic pressure changes. Where's my eraser? And now we will talk about the second law of thermodynamics. The second law of thermodynamics is the most interesting one. And it is about, you've probably heard references to entropy. This has to do with the second law of thermodynamics. Second law of thermodynamics. Heat will never, of itself, on its own, flow from a colder object to a hotter object. Remember, heat always wants to go from the hotter object to the colder object. Now, with a refrigerator, it's not doing it on its own. You unplug that refrigerator, it will get just as warm as the room that it's in. You plug it in, work is being put to keep doing that fancy schmancy thing with the circulation and the coils to basically trick it into pumping that heat out. But you unplug it, you stop putting your external work in, and it's just going to heat up. Why? Because heat will never on its own, this is the key word here, on its own, heat will never on its own flow from a cold object to a hot object. This is why you don't put an ice cube in the sun and expect that it's going to freeze even more. You don't put a ice cream cone on top of a hot piece of cake, or a scoop of ice cream on a hot piece of cake, and expect that the ice cream will get colder. Like that's not going to happen. Like the heat from the cake, warm hot cake, will flow into the ice cream and melt it. Because heat we never expect it on its own to flow from a cold object to a hot object. Because remember, heat, the definition of heat is that thermal transfer from a hotter temperature item to a cooler temperature item. That's the definition of heat. So another way of saying this, a fancier schmancier way of saying it, and I'm going to read it from here because I like how he says it some places here, is that when work is... So we're going to take this second law of thermodynamics and apply it to heat engines. So what is a heat engine? A heat engine is any engine that basically uses how heat is traveling from a hot temperature to a cool temperature to turn some of that into work. To usable work. So the steam engine, for example, remember that it would heat it up, the water, and then it would boil, and then it would push the piston up, and if you've ever seen those old-fashioned trains, and it would push, and then and then round and round and round, and so it's using the heat to turn the wheels of that steam engine. And then later we have our other kinds of heat engines in our cars, and that is using the heat of the burning of the internal combustion engine, burning the gasoline to turn that piston up and down, make your pistons fire, and then that's what turns your wheels and all that. Or a jet engine. A jet engine is burning up that fuel, shooting out behind, and then the momentum, conservation of momentum. Wait, I'm almost done. And it's shooting your jet forward. So in all these things, you're taking work. I'll help you later. You're using that natural flow of heat from a higher temperature, they call reservoir, a higher temperature reservoir to cooler temperature reservoir, and you're somehow using some of that to turn it into work. So this is how a heat engine works. So jet engines, internal combustion engines, all of that, those are heat engines. And they're going from the hot reservoir to the cool reservoir, and some of that is becoming work. Now, what the second law of thermodynamics teaches us about heat engines is that basically you are never going to get all of this energy to turn into work. Some of it is going to go here. Some of it is going to be wasted as heat exhaust. Some of it, or wasted from, now was it wasted? Well, if you're using that heat exhaust, say to warm up your greenhouse in Siberia, then you're very happy about it. If you live in the middle of Arizona and you've got all this heat exhaust and it's 115 degrees outside, then well, you're not happy about that extra heat exhaust. So that's, is it truly wasted? Well, it depends what you do with it, et cetera, but I mean, how you see it. It is from a thermodynamic perspective going from a higher state, getting lost. But yeah, you can do things with it. But anyways, so back to when work is done by a heat engine running between two temperatures, temperature of the hot reservoir and the temperature of the cool reservoir, is that all of that input heat cannot be converted purely to work. Some of it will be expelled as the extra excess heat into the cold reservoir. And you say, well, how much? And Carnot, this French engineer, figured out exactly how much. He said the best, so if you had no friction in your engine, no other problems, it's working absolutely perfectly well, which almost no engines really are, but if you had a perfectly ideally efficient heat engine, now this applies to heat engines, the ideal efficiency would be the temperature of your hot reservoir minus the temperature of your cold reservoir, so the difference in their temperatures, divided by the temperature of your hot reservoir. So, they give an example in the book. If your hot reservoir is 400 Kelvin, your cold reservoir is 300 Kelvin, so you've got 400 minus 300, and your hot reservoir, again, is 400 Kelvin. You're getting 1/4, so you're getting 25% efficiency. So you can see that if you want a more efficient engine, you want your hot reservoir, your cold reservoir to have a bigger and bigger and bigger difference between them, as much as you can possibly make it. And that's why he talks about how people have this dream of making ceramic engines. Right now, ceramic isn't tough enough to build your engine out of. You have to do that out of metal. But building our engines out of metal has a upper limit on how hot, when we're trying to crank that difference up between these two guys, how hot we can make our, when we're trying to crank up this difference, how hot we can make the hot reservoir, because metal melts at a certain temperature. Ceramic won't melt at that temperature that metal will. So theoretically, if we could make ceramic engines, we could make that temperature so hot that we can crank better efficiency out of our heat engines. So that is the second law of thermodynamics applied to heat engines. And he's got some pretty cool illustrations here. We won't go deeply into detail on this. How steam turbines work. It's very worth a read. Okay, so now we're going to keep talking about our second law of thermodynamics. This was how it's applied to heat engines. And we're going to, what did I do? So another way to say it, the way that you probably hear about it the most, is natural systems. So this is not a system where you are pumping in work or effort or, new stuff like the fridge. This is a natural system. So a system left to itself, without a human intervening, without some intelligent person intervening. Natural systems tend to proceed toward a state of disorder. Everything loses order. I mean, you know this, if you've ever had kids in a room and they mess it up, you throw them on the floor over time. If you look at things tend toward a state of disorder. They don't spontaneously, become more ordered. They become less ordered over time. I really like how he says it in the book here. Disordered energy can be changed to ordered energy only at the expense of some organizational effort or work input, some intelligence, some attempt to change it to, make it more ordered. For example, air can be ordered into a smaller region by using a compressor, but without some work input, no increase in order occurs. In the broadest sense, the message of the second law of thermodynamics is that tendency of the universe and all that is in it tends toward disorder. So this is, if you've heard entropy, if you've heard the term entropy. Entropy is disorder, unusable energy, things falling apart. And the second law states that for natural processes, in the long run, entropy always increases. That the entropy is always, gas molecules escape from a bottle and they move from a relatively ordered state to a disorderly state. Organized structures become disorganized messes. Things left to themselves run down. When a physical system is allowed to distribute its energy freely, it always does so in a manner such that entropy increases while the available energy of the system for doing work decreases. This is just what, yes.
Wait, was the world always like this?
In
Having
the
like
words
this-
of someone, it's almost like a wind-up toy that you've wound
Yeah.
up and it's using up what it has. It's winding down.
In heaven, is that not gonna be?
Well, that's a philosophical question. Although this is also a philosophical question. This is very, philosophical. It's talking about this. That the universe tends toward less, toward losing information, toward things falling apart. The exception that we see that is with life. That your body is constantly trying to make order out of disorder. Life is always trying to, arrange your proteins. I mean, even we end up succumbing to entropy. But, your life and information is that information gets degraded over time. This is a lot of interesting philosophical ramifications, implications. There's been so much said about this. I highly encourage you to look into information theory. And there's a lot to unpack here. There's a lot about like the origins of life, the origins of the universe, all of that. There's a lot to unpack here because as you can see, natural systems tend to proceed toward a state of disorder, doesn't mesh all that well with the theory of evolution, because the theory of evolution is all about spontaneously, with no direction, with no intelligent input, things proceeded from a state of disorder to order. What makes a lot more sense is that, super genius aliens were, sticking information
Wait,
in.
you think that happened?
Hold on a second. There are people that argue this. Is super genius aliens were actually putting information in to make things, create things. At some point, there's not really any difference between the super genius aliens and the gods.
Or
God. So it is very fascinating here that we start out with heat pumps and whatnot, and we end up by talking about the origins of information, the origins of the universe. I highly encourage you to look into information theory. There are some really cool books about the origins of the universe. Information theory, I think, like Michael Behe writes a lot about it. Stephen C. Myers. There's just a lot of people that talk about these questions, especially when it relates to information. Because what we learn from second law of thermodynamics is that information degrades unless there is intent, unless there's purpose, unless there is like an input. So that was something pretty cool. And then the last bit, or one last thing I wanted to say on chapter 300, page 367, when he talks about thermal pollution, I thought it was a little bit disingenuous, and that he's talking like, thermal pollution is this just terrible thing that, there's nothing we can do to change. Worrying about the thermal pollution of a power plant, like directly, like if it's in your backyard, yes, it's going to make it hotter. You know what I mean? The thermal, but worrying about it from a global scale, like the sun is putting such a massive amount of heat into our Earth. Like the numbers, like it sounds plausible when you read it. A physicist knows better. When you plug the actual numbers in, like, I don't know, this is kind of like saying your 2-year-old sister is going to knock the house down by thumping on a wall if your house is built out of solid rock. The amount of the thermal byproduct of our energy plants and whatnot, like it affects the near radius or the near where it's near, but it doesn't, like if you're talking from a global scale, like the thermal energy of the sun being massive amount being pumped into the earth. Like if you put the numbers in, yeah, this is not like a global problem. This is more a local problem. Okay, I think that's all I had to say on chapter 24. Thank you. Stop.